Okay, for this video I'll be going through chapter 18 for pure physics electromagnetism tutorial. Okay, the first question they want us to it shows cross section of two wires A and B carrying currents of 1 ampere and 3 ampere. So you must note that whenever current flow, it will produce a magnetic field. Okay. So of course the current, the wires carrying current of 1 ampere will produce a weaker magnetic field than the wire that is carrying current of 3 ampere. So basically a larger current will produce a stronger magnetic field. And how do we represent a stronger magnetic field? Is by drawing the lines to be closer together. Okay, so if we were to look at wire A, we are looking at the cross-sectional area. Okay, so the X would actually mean that the current is going into the page. X means going into the page. So we need to use the right-hand grid rule for solenoid. Okay, and what does the thumb represent? The thumb represents the direction of current. And therefore, if you are looking at the screen, your thumb should be pointing into the screen. Okay, and therefore your fingers will be curled up because you are gripping it and into a clockwise direction. So that's why we have current flowing in this clockwise direction. Okay, so now we take a look at wire B, which carries a current of 3 ampere, stronger magnetic field. So again, your right hand thumb is pointing into the screen. So again, we have current in this direction. Okay, in a clockwise direction. Now, because the magnetic fields cannot cut each other and cannot touch each other, so if you look at over this area, the magnetic field is actually opposite in direction. So therefore, there will be a void. But over here, because the magnetic field is in this direction, so they will merge to look like this shape. Okay, so it will be something like that. And if we want to know the force acting on the wires A and B, okay, so obviously we have more magnetic fields here and in the center, because they are in the opposite direction. For the magnetic field of A and magnetic field of B in the center, they are in the opposite direction. So if they are in the opposite direction, yeah, therefore they will cancel each other out. Therefore, we will have less magnetic field over here. So the force is always from more to less. More to less. Okay, therefore the force is towards the center. Now, of course, you can also use Fleming left-hand rule to find the force. Okay, so maybe I redraw. So this is A, and this is the magnetic field produced by A. I'll use another color for B. Okay, the current is into the page, so the magnetic field is also clockwise. Okay, so if we want to apply Fleming left-hand rule, where the thumb represents the force, the first finger represents the external magnetic field, and your middle finger represents your current. So if you want to find the force acting on B, okay, so we will take our middle finger and point into the screen, because that is the direction of the current. It is into the page. Okay, but the external magnetic field is actually from A. A is producing a magnetic field, and it is the external magnetic field for B. So your first finger will be pointing downwards to the bottom, whereas your middle finger will be pointing into the page, right? And your thumb will then be pointing to the left, and therefore the force on B is to the left. You can apply this for A and you will get the same answer as this. Okay. Okay, question 2. A metal rod AB is placed on two smooth horizontal metal rails fixed on the bench as shown. So these are the metal rails. Okay. The set of crosses, important, represents a uniform magnetic field. So now there's an external magnetic field, right? What happens when switch S is closed? So when switch S is closed, current will start to flow in this direction because this is the positive. The longer terminal, the longer side is the positive terminal, so current will flow through the rail and go from A to B and then back to the battery again. Okay, so now we have a current flow, and when current flow, it will produce a magnetic field. In the presence of an external magnetic field, there will be a force. Okay, so the current will now flow in a metal rod AB. The interactions between the uniform magnetic field, this one is the external magnetic field, and the magnetic field due to the current carrying rod AB will produce a magnetic force on rod AB. Now, the reason why there's a force is due to the interaction of the magnetic fields. Okay, so if we were to use Fleming left hand rule, we will know that the force will cause AB to move to the right. Why is there a force on AB? Due to the interaction of the magnetic fields. How do we know the direction? Is by Fleming left hand rule. So this is how we know how to know direction. Okay, but why is there a force? Is due to the interaction. Okay, so these are different kind of questions. Now explain the effect on the motion of the rod AB if the magnetic field strength is increased. So of course there will be more interactions, right? Therefore AB will move to the right with a larger acceleration because there will be a larger force. What will happen if the separation between the rails is increased? So we will also have a larger magnetic force produced, as now a longer length will have will be now within this uniform magnetic field, so therefore more interactions of magnetic field, so AB will move to the right with larger acceleration because there will now be a larger force. Now suggest one way to reverse the direction of the motion of rod AB. We can either reverse the direction of current or reverse the direction of the magnetic field. Okay, question 3. A conducting rod AB is suspended horizontally by two spring balances in the magnetic fields produced by a pair of magnets, so X and Y. Now, when the switch is closed, the reading of the spring balance decreases. That means instead of pulling it down, it goes up slightly, right? Because now there will be a force whenever current flows, right? It produces a magnetic field, so this current will flow in this direction, and this current will produce a magnetic field which will then interact with the external magnetic fields. Okay, so I like to convert it into 2D diagram. So if I am looking from this perspective, okay, I will see not the whole length of the wire. Instead, I will just see this cross-sectional area. Okay, and I know that the current is going away from me, away from my eyes, so I will use a cross to represent. And according to the question, I know that there is a force acting upwards. Why? Because the spring balance reading decreases. So now I have force, I have current, I can actually find the direction of the external magnetic field. So I'll use Fleming left hand rule. If you're looking at the screen now, my thumb is pointing upwards like the force. My current is my middle finger is pointing into the page. So that means my first finger is pointing from right to left. Okay, and magnetic field lines always comes out from north and enters the south. Therefore, X is south while Y is north. So this is how we determine the poles. Now, suppose the cell is replaced by an AC source of 5 Hz. That means the direction of the current will change 5 times per second. Okay, so what will happen to the motion of the rod? So the rod will actually oscillate up and down because we change the direction of the current. Then your Fleming left hand, the middle finger will be pointing in and out. Okay, at a frequency of 5 Hz. Okay, question 4, a simple motor is shown. So whenever you see motor, you know you have to use Fleming left hand rule. Okay, whenever you see generator, you have to use Fleming right hand rule. Okay, so generator is we give force, we get current. Motor is the other way. Okay, we give current, right, and there will be a force produced. Okay, so these are the basic difference between Fleming left hand and right hand, motor versus generator. Okay, so the solenoid and the coil PQRS are connected in parallel to a battery. The coil can rotate freely about the horizontal axis XY. Now state the pole of the solenoid at B and at C. Okay, so let us examine how the current flows, positive, negative here. So current flows here, okay, and current flows here and flow here, right? Because it's parallel. So it'll flow into the carbon brush, and this is the split ring of side PQ. Okay, so the current will flow in from P to Q. Now on the other side, this blue color split ring, it is the split ring of RS. Okay, so please take note that the split ring, they will not change the side of the coil, meaning if this part, the purple one, is for PQ, it will always be attached to PQ. Okay, no way that PQ can come into contact with the blue split ring. Okay, so this is what I mean. So the current will actually flow from R to S, right? And then back through here, down, and back to here. Okay, but we also have current that flows into the solenoid here. So over here, when current flow, it produces a magnetic field, but this is in a solenoid, so we have to use right hand grip rule for solenoid. So for solenoid, the fingers represent the current, the thumb represents the north. Therefore, B will be a north pole. Okay, and the current continues flowing to this way. Okay, so this is very important. The little arrows that we are drawing over here will tell you how to grip your apply your right hand grip rule. Okay, so your fingers represent the direction of the current, and your thumb represents the direction of where the north is. So C will be a south pole. Okay, so if I were to, they want us to see what is the direction of rotation of the coil as seen from Y. That means if I look from this direction from Y, okay, how is it turning? So of course this thing is like a 3D thing. So again, I will convert it into a 2D. So I have a north and south here. So this is my B, this is my C, and I don't see this as a whole length PQ. Okay, rather I see the cross sectional, and this is my RS. So the direction of current is from P to Q, so it is away from me because my eye is looking in this direction, from Y direction, and the current that's flowing in the RS arm is flowing from R to S, so it's going to be a dot. Okay, so now we can apply Fleming left hand rule. So I'll do it for PQ. So my middle finger is pointing into the screen. Okay, if you're looking at the screen, your middle finger should be pointing towards the screen. And because there's a external magnetic field N to S, so my first finger, which represents the direction of the external magnetic field, is pointing from left to right, and my force is downwards. Okay, and because the current flows in the opposite direction, so RS, the force on RS will be to the top of the page, and in this case it will become anti-clockwise. Okay, now name the component E and state its function. Very simple, it's a split ring commutator, not to be confused with slip ring. Now the purpose is to reverse the direction of the coil every half a revolution so that the coil continues to turn in the same direction. Okay, suggest two ways to increase the turning effect, so you can read it by yourself. Okay, so one thing that you need to take note of is not to say the number of coils, is the number of turns of the coil. Okay. Okay, question 5. In each of the following case, determine the direction of rotation. So this is where we apply Fleming left hand rule. So I would like to convert it into a 2D diagram again. So this is a dot, this is a cross. Whenever I convert it into 2D, I find it easier for me to apply my Fleming left hand. Okay, so north south, so this is down, this is up, so therefore it is clockwise. Okay, then how about this? How do I convert it? North and then south. Okay, so I will just have current this way, and current on the other side is this way. Okay, no problem, I can still apply my Fleming, just that my if I'm doing on this side, my middle finger is pointing to the bottom of the screen, north to south is this way, and the force, you will see that your thumb is pointing towards you, so this is the direction of the force. Okay, and so over here will be opposite direction. So if we were to see it from the top, then it will be a anti-clockwise direction. Okay. Okay, last question. Figure 6.1 shows a simple milliammeter. So X and Y are the terminals of the meter. The pointer points to the 0 meter when no current flows. Okay, so this diagram is a little bit complex because when AD is the arm AD is it is turning, right? It's moving. Let's say it moves into the page, the force, okay, on AB, and therefore BC must be turning in the opposite direction, right? So this is force on BC. This is AD, sorry. Okay, so it will cause this pointer to rotate. Okay, so this is how it works. It is not drawn very clearly, okay, but this is how you should interpret it. Now, part A, a current is flowing through the coil and the deflection of the pointer is shown. What is the direction of the current in the left side of the coil, A to D or D to A? Okay, so we know that it is rotating it in this direction. Therefore, force on AD must be into the page. Okay, force on BC would be out of the page. So we can then apply our Fleming left hand rule. So again, let's draw a 2D diagram. South, then this is the wire. Okay, this is the wire AD. This is the wire BC. Okay, so I know that the force on AD is coming out of into the page, because it is rotating in this direction, and for BC it is out of the page. Okay, so since I know the force, I will need to use my thumb. Okay, I find it easier to do on BC lah. Okay, because the thumb for me right now is pointing to myself. Okay, because the thumb represents the force, and the external magnetic field is from north to south. So my first finger is actually pointing from left to right. My thumb is actually pointing towards myself, and my middle finger is actually pointing to the bottom. So I know the current is flowing from B to C, and therefore the current must be flowing from D to A. Okay. So this looks a little bit complex, but you can ask me in class to show you physically. And I can show you. Okay, now suggest two ways to increase the sensitivity of the milliammeter. What is the purpose of that milliammeter? It is to measure current. So you cannot say, oh, increase the current, because by increasing the current, it is what we are measuring, right? We just want to increase the sensitivity. So the correct answers will be increase the number of turns of the coil and not the number of coils. Okay, increase the number of turns. When I have more turns and when a current flows through, even though it's a small current than before, but because I have more turn, there'll be more interaction with the external magnetic field, so it will be more sensitive. Or I can increase the strength of the magnet, or I can insert a soft iron core. Okay, but you cannot say increase the current, because in this case we are actually measuring the current. Now, explain briefly how the milliammeter measures the current. So the interaction between the magnetic fields created by the current carrying coil, right? So there is one magnetic field that's produced by the current, and there is also an external magnetic field by the magnet. So it is the interaction that produces a magnetic force. Okay, so when the current is increased, the force created will be stronger because of a stronger magnetic field that's produced, and when I have a stronger force on both sides, opposite direction, the turning effect increases, so the pointer will turn further and point to a higher current value. Okay.